Hello, everybody. So today we're going to talk about one of the aspects of our problem-solving strategy for solving problems using forces. And it is this very last step on here about reflecting on our answer, and in particular, how we can evaluate an answer using special cases. Now, special cases, in fact, are not something that is necessarily unique to the forces side of things. And in fact, the example I'm going to do in a minute is not going to be a forces example, but it is a particularly powerful thing to do when you have forces problems, because we typically have a lot of interesting variables to investigate in a forces problem. So with that said, I'm going to dive right in. This is how kind of special case analysis works. You want to think about what quantities are in your solution to something, and you want to choose a case that is special, not a case that is arbitrary. And the difference there is it can be tempting to say, oh, I know what should happen when I plug in theta equals 30 degrees, or I want to know what should happen when I plug in theta equals 30 degrees. But unless you've got a really good reason for why that is special, why you know the answer to that 30-degree situation right off the top of your head, then that's arbitrary and not special. Once you kind of have chosen a special case, you want to try to figure out what your quantity should be in the case that you chose. What that usually looks like is kind of simplifying your situation to something where you, like I said, can look at it and be like, oh yeah, I know what the answer ought to be. Once you've done that, you want to try to identify the value of one or more of the other quantities that correspond to your case. We're going to do an angle today. Evaluate your answer in that special case. And then kind of most importantly at the end here, check to see if our two strategies, right, figuring out what our answer should be and figuring out what our answer says, actually agree with each other, right? So the example that I'm going to do here, I got lots of space for us to work, is I'm going to think about an old situation that we did a couple of weeks ago, which is if I throw a ball on a flat field and I know how fast it's going and the initial speed of the ball, the initial angle of the ball, can I figure out how far the ball has gone? So I'm going to draw a quick picture of this situation just so everybody kind of knows what I mean. So I've got my initial velocity vector here, and then the ball is, maybe I'll do the ball in green because it's a tennis ball, right? It kind of follows a little trajectory here and it hits the ground over here. And the thing that I might be looking for in a problem like this is how far did the ball go, right? So I might write that as D. Now we solved this problem a couple weeks ago. I'm not going to spend time here solving it again. I'm just going to look up what the answer is. And that answer ends up being that this distance D is given by the speed squared times the sine of 2 theta, where theta is this angle here from the horizontal, divided by little g, which is the acceleration due to gravity. Right? So that's my equation for how far this ball will go when I throw it on flat ground. So the thing we're here to do today is to investigate this answer using a special case. And I'm going to kind of flash us quickly back over to our kind of steps for special case analysis, right? We want to choose a case that is special, not arbitrary. Again, 30 degrees here is not special. I don't know what should happen in the 30-degree case. But there are a couple of cases here that are very special. And those cases are if I set theta equal to 0 and if I set theta equal to 90. And I'm going to tell you a little bit about why I think those are special cases. And I'm going to do it by thinking about the physical situation, right? So I'm throwing this ball and I'm throwing it at an angle, right? If I throw it at kind of horizontally, I am not going to throw the ball very far. In particular, the assumption we made when we solved this problem a couple weeks ago was that the ground was at the same height as the ball started at. So what I'm really doing is not throwing it from up here, going all the way down to the ground and throwing it kind of like this. Okay? And what that means is when I throw the ball at this angle, it's not going anywhere, right? Even though I throw it really fast, it hits the ground right away and doesn't travel anywhere. So my expectation physically is the D is going to be 0 in this case. The same sort of thing happens if I think about, what if instead of throwing it this way, I throw it straight up in the air, right? And I'm going to think about that. This one I can actually do, right? I throw it straight up in the air and it comes back down and I catch it right where it started, right? If I throw it straight up in the air, it's not going to go that way. It's not going to travel any horizontal distance. So I again expect that my answer here ought to be 0. Right? Again, I haven't touched this equation yet. I'm just thinking about what my expectations are. Now I'm going to go to the equation and fill out those other steps, right? Which is I can plug in theta equals 0 and theta equals 90 to my expression and see what I get. And that means I need to know something about how the sine function works, because in the first case, I'm going to get sine of 0, which I do happen to know is 0. And in the other case, I'm going to get sine of 2 times 90, which is 180 degrees, which also happens to be 0. Right? So in both of these cases, that trig function, the sine of 2 theta, gives me 0. And it doesn't matter what v is, and it doesn't matter what g is. I'm going to get that the distance traveled is also 0. Right? So my math is telling me that d is equal to 0 in both of these situations. And I can see in both cases, yes, I am getting the same answer from the mathematics at the end as I am from my physical intuition and understanding of the question. And that, everybody, is special case analysis.